This presentation is entitled Process Management. In this presentation, we demonstrate clever use of Divine Inspiration's powerful TCSQL technology in support of process management. In this presentation, you'll see how to capture a process definition and then turn around to instantiate the process to create a project plan. This powerful capability, to the best of our knowledge, does not exist anywhere today.
Process management. The application mentioned on the previous slide is founded by a powerful technology called TCSQL, which features the ability to maintain graphs, particularly with a powerful capability called transitive closure, features the notion of something called a soft schema. We're going to start by doing a little graph theory here. In front of us are two graphs, a family tree and a graph of bus routes. Some of the components of a graph consist of the following: the notion of something called nodes. In this family tree graph, the nodes happen to be the names of people here. A second component of graphs are these things called connections here, or edges. And they happen to be the arrows we see between nodes here. Sometimes in graphs, you have a semantic relationship associated with these arrows. In this family tree graph, we have a father of relationship and we have a mother of relationship. Sometimes with graphs, you have scalar values associated with the connections. In this bus routes example, the scalar value represents a cost of going from one city to another. The object-oriented paradigm can be represented as a graph problem. So here we have a class here called class 1, which has properties A, B, and C, and a hazard relationship between the class definition and its associated properties. We also have another class here called class 1.1 with properties D and E. And we see a relationship here between these two nodes, an is-a relationship, meaning that class 1.1 is a specialization of class 1. Now let's look at a graph here. Let's look at what happens if we want to instantiate class 1.1. Let's look at the equivalent object graph. In this case, it would look like the following. Assuming we want to instantiate class 1.1 and we're going to call that object 1, what happens is the following. We first want to instantiate properties D and E, and then we want to look at this inheritance is-a link here to inherit properties A, B, and C, which is what you see down here. Okay, now let's look at the relational tables needed to support this paradigm here. So we have the notion of a class table here, which represents the nodes of our class graph here. It's basically a name-value pair here, and we have a type column here, and legal type values. This represents basic class types here. We have a class connection table of parent-child nodes here and a connection type here. In this case, it's going to be either has-a or is-a. And then we have a transitive closure table representing the transitive closure of this class graph. And assume for a minute that this transitive closure table is automatically populated and managed whenever nodes or connections are added or deleted in this class graph. Let's look at the tables needed to support our object graph here. We have a table called object, which represents the nodes of our object graph here. Again, it is basically a name-value pair with a class column here representing the kind of class that we're instantiating here, including the class properties. We also have an object connection table here, which represents the connections of our object graph. So it's a parent-child pair, again with connection type. And we have a transitive closure table associated with our object graph. And assume here also that this transitive closure table is maintained automatically whenever nodes or connections are added or deleted in our object graph here. So this whole paradigm here I'm describing here with these 6 relational database tables is something known as a soft schema. With this soft scheme model, let's look at an example of instantiating a class instance here. So we have a class graph here, and all the data in this graph can be represented with two tables here. So we have a class table representing all of the nodes of this graph. We have a class connection table showing all of the connections here. Now I didn't bother showing all of them. I just showed a few of the rows here. Okay, now let's look at what happens when we want to instantiate this particular node here, a boy. What we're going to do is instantiate this boy. We're going to call this instantiation Andy here. And what is going to happen behind the scenes is TCSQL is going to figure out all of the particular properties that need to be inherited here, and it will populate appropriate object and object connection tables here. And these two tables will represent an object graph that looks like the following here. Notice here that I've introduced a new kind of relationship, a has-not relationship. TCSQL supports the ability to do inheritance override here. Now, if you were to implement this in an object-oriented language such as C# or Java, this is the object graph equivalent what you would get here. Now, the real power and beauty here is I did this directly in a relational database using standard SQL. The use of TCSQL provides the ability to develop rather sophisticated applications. For the application featured in this presentation, we're going to use a schema consisting of the following. A couple conventional relational tables here, one for time card records and one for personnel records, and we'll use the notion of a soft schema to represent the data in graphs. Let's look at how to apply the TCSQL capabilities talked about in the previous slides toward developing a process/project management application. So imagine the following here. We have a house that we want to build, and the house is broken down into first floor and second floor, broken down into various rooms. And so what we're going to utilize here is the notion of a work breakdown structure. And each work breakdown structure node is broken down into smaller chunks of work here, as you see. And assume that at each level of abstraction here, there's a number of attributes associated with that level of abstraction, namely a collection of tasks that must be accomplished, and assume there's a temporal relationship between the tasks. And so, in effect, what we're going to be constructing is a little mini task network associated for each level here. So let's now define a process for creating a house. So we'll start out with the notion of a house entity. So this will become a record in the class table. We have the notion of a floor and a connection between the two, a work breakdown structure connection. A floor will be broken down into one or more rooms here, so these are all records in our class table here. We'll introduce the notion of a task here. And the task will have a property, it has a property. In this case, it's called estimated duration. A second property called actual duration. And we'll introduce a new kind of connection here called a temporal connection here. And here we're doing something different, something we haven't seen in any other presentation. We're going to introduce an attribute associated with a connection called delay. And we're going to introduce an entity here called T9, which turns out to be, is a relationship, so T9 is a task. Similarly, we're introducing this thing called T10, and T10 is a task. And we're going to create a temporal relationship between T9 and T10, meaning in order to start task T10, T9 must first complete. Now we want to connect T9 as a task, a part of this higher level entity called a room. So we have has a relationship here. Similarly, we're going to connect T10 as has a property of room here. So now we defined a room here. So we will do something similar with defining a floor, and continuing we will do something similar with defining the tasks associated with this entity called a house. Okay, let's now look at our finished process definition here. So in the last slide you saw we were putting together a definition of a room which had tasks T9 and T10 and the temporal relationship between them. So here's our floor definition, and here's our definition for our higher level entity called a house here. And notice that here we have a task called T1.1, which is a specialization of a more general task called T1. Similarly, we have task 3.1, which is a specialization of a more general task called T3. And we have this temporal relationship here between these general tasks here. Notice also that we have temporal relationships between tasks that cross entity boundaries here. So let's assume now we would like to create a project plan by instantiating our process definition. So let's assume we would first like to instantiate our house entity here, and we're going to call this instance my house. So the name is my of type house. And what TCSQL will do behind the scenes is instantiate all of the tasks that define our house entity here. Notice though that what appears in this circle here is slightly different than what appears in our template here because of the following. In our template definition, we had this temporal relationship between these general tasks here. Well, what happened when we instantiated this entity is TCSQL was smart enough to realize that there needs to be this behavior inherited between these two tasks. So now we have a temporal relationship between task T1.1 and task T3.1. Let's assume now we would like to instantiate a floor, and we're going to call it first. So we insert into our object table, naming it first of type floor. And TCSQL behind the scenes will instantiate our tasks here and the temporal relationships between them. Assume now we would like to connect our first floor to our house here. So we're going to insert into our object connection table. And what TCSQL will do behind the scenes is connect up the tasks that cross entity boundaries here, this temporal relationship here. Continuing, let's assume we would like to instantiate a room, and let's call it a kitchen. So here we're inserting into our object table again, calling it kitchen of type room. And again, TCSQL behind the scenes will instantiate our tasks here and create a temporal relationship. Let's assume we would like to connect our kitchen to our first floor here. So we insert into our object connection table. And again, TCSQL behind the scenes will connect our tasks that cross entity boundaries here. Now look what we have accomplished here. In a mere 1, 2, 3, 4, 5 insert statements in the appropriate tables, we've instantiated a project here. We've instantiated our process definition here. So we've in fact introduced a new paradigm, a very powerful way of defining and instantiating a project plan. So why is this valuable? First of all, I claimed I was able to demonstrate the ability to think in terms of a higher level of abstraction. So if we predefined an entity such as a house in instantiating it, we automatically get its definition instantiated automatically for us. A task network is generated automatically from this higher level of abstraction. So in effect, we're able to create a PERT chart by instantiating this process definition. And because we are instantiating a process definition, we've predefined it, the project plan is going to be correct by construction.